So today's lesson is on parallel circuits. Specifically, we're going to look at Kirchhoff's current and voltage laws for parallel circuits and how to calculate equivalent resistance in a parallel circuit. So let's start with current. So current, we have a whole bunch of electrons moving through a parallel circuit. So here we have a parallel circuit with two resistors in parallel and our power source. And as all of these electrons start moving, and we get to an intersection here, they have a choice. And some will choose to go this way, and some will choose to go this way. So what happens is that current gets split. And you can think of it as this water wheel where suddenly two different pathways, you have a different amount of water going down each pathway. Okay? And because we have water going down each pathway, they're no longer the same like they were in series circuits. But what happens is they eventually come back together. And so we can say the current that goes through the battery is equal to the current that goes through our first resistor here, plus the current that goes through our second resistor. So this is the opposite as Kirchhoff's current rule for a series circuit. For a series circuit, it was the same throughout, but for a parallel circuit, our total current is going to be the sum of the current across each branch of our parallel circuit. Now for voltage, however, let's follow one electron. So one electron, let's say, picks up a certain amount of energy at the battery. Let's say it's a 9-volt battery, for example. And that one single electron has a choice. That one single electron might choose to go this way. If it goes this way, it's only going through that one resistor. Therefore, it's going to give up all of its energy, all 9 volts, to this resistor. Let's follow a different electron now. A different electron made a different choice and chose to go this way, through this resistor. Now this electron is also only going through one resistor and will give up all of its energy at that resistor. So what does this mean? It means that the voltage across the branches in a parallel circuit are the same. So if this is 9 volts, then those electrons that choose this path will give up 9 volts here, and the electrons that choose this path will give up 9 volts here. So Kirchhoff's voltage rule for a parallel circuit is that the total voltage equals the voltage through the first branch, which is the same as the voltage through the second branch, and so on and so on and so on for however many branches your parallel circuit has. So now let's talk about equivalent resistance in a parallel circuit, meaning if I were to redraw this circuit here and replace those two resistors with one resistor, and that one resistor has an equivalent resistance to both of those resistors put together, what is that equivalent resistance? Okay. So let's say you're on a country road and there's one lane. Okay. And you have a whole bunch of cars. It's a lot of traffic building up there. Now what if you open 2 lanes? So now you have 2 possible lanes each car could go in. It actually reduces the amount of traffic. What if you opened up 3 lanes, 4, 5, 6 lanes? Now you've reduced the traffic so much you've got those cars speeding down towards their destination. This is what happens here. The more sort of lanes or branches that we open up, oh, that wasn't my laser, the more branches that we open up, we reduce the total resistance in the circuit, which increases the total current in the circuit. Right? So our equivalent here is going to be actually less than either of these resistors on their own. So what do I mean? If this is, let's say this is 10 ohms. Let's actually just write an example here. Let's say this is 10 ohms and this is 10 ohms. To figure out equivalent resistance, this is the equation we're going to use. So 1 over R total, or R equivalent, whichever you like to use, is going to be 1 over 10 plus 1 over 10. If you add those fractions together, we get 2 over 10, which is the same as 1 over 5. So our total equals 1 over 5. Now, 1 over 5 doesn't equal our total. It equals 1 over our total. So we sort of need to flip each fraction on each side. So that would leave our total as equaling 5 ohms. So we now have less resistance. So imagine we didn't have this second resistor. The total resistance in the circuit would be 10. If we added another load in parallel with the exact same resistor, now your total resistance in the circuit is 5. It decreased, meaning you have more current running through there. And that can be dangerous. We'll talk more about safety in another lesson, but I'm sure you've all heard the more things you plug into an outlet, because outlets are all in parallel, the more you plug into an outlet, the more dangerous it is. The reason is because you're reducing the resistance in the circuit, which increases the current, and the more current you have going through that circuit, the more heat is produced, which could eventually start a fire. But we'll also talk about things like circuit breakers and fuses when we do our lesson on safety. But does anyone have any questions with this up till now? So here's our first example then, and this will be our intermediate Sudoku puzzle. Okay. We have a parallel circuit. The total voltage is 240 volts. Our first resistor, R1, is 400 ohms, and our second resistor, R2, is 100 ohms. So the first thing we can solve for, since we know the resistance of both resistors, we can find the total resistance. And because it's a parallel circuit, we're going to do 1 over R total equals 1 over 400 ohms plus 1 over 100 ohms. Now we just need to add fractions. I'll do it in a couple steps because I know people don't like fractions. So 1 over 400, and I'm just going to change this denominator to 400 as well. So that would be the same as writing 4 over 400. So now we have 1 over RT equals 5 over 400. Or, if we flip them, so RT over 1 then equals 400 ohms over 5, which reduces RT to being 80 ohms. So we know the total resistance then is 80 ohms. And it makes sense, because like I said, with a parallel circuit, your total resistance should be less than either of the resistors in your parallel circuit. All right, next step of the puzzle. Since we have two pieces of information here, we can use Ohm's law to solve for the third. Remember, Ohm's law is delta V equals IR. So here I know delta V and R, so I'm going to rearrange to solve for I. So I total equals our total potential difference divided by our total resistance, which is 240 volts divided by 80 ohms. So that gives us 3 amps. All right, so we know we have 3 amps here as well. Next step of the puzzle. This is a parallel circuit. Now, current is not the same in a parallel circuit. This could be 2, this could be 1, this could be 1, that could be 2, or this could be 1.5, and that could be 1.5. We know they should add to 3, but that's not enough information for me to determine which is which. However, in a parallel circuit, Kirchhoff's voltage law says the voltage is the same. So I know this is going to have 240 volts going through it, and this is going to have 240 volts going through it. So now that I have two pieces of information for each resistor, I can go back to Ohm's law to figure out the missing third piece, which is again current. So to figure out current, I am just going to do voltage divided by resistance. So for the first one, we have 240 divided by 400, which gives us 0.6 amps. And for the second one, we have 240 divided by 100, which gives us 2.4 amps. And we can do a check on that. We can use Kirchhoff's current law for a parallel circuit, which says that these two currents must add to give the total current. And indeed it does. 2.4 amps plus 0.6 amps do add to 3 amps. So we've solved all of our unknowns in our circuit.